Okay, so welcome back. Uh, so we are trying to make you understand some basic principles of orientation representation using Quaternion. And that is very important because this is not in robotics and any rigid body orientation. This is widely being used nowadays, thanks because of its programming ease. And as I told you, that robot gripper orientation is very much prone to, or in some cases, very much prone to gimbal lock because of the construction itself. Three joint axes are intersecting at a point to follow Piper's recommendation. Robotics people know. We try to follow industrial robot, try to follow Piper's recommendation so as to get closed form inverse kinematic solution. And in doing so, this is vulnerable. So when a particular pose is given and your gripper is trying to orient itself with that pose, so it is vulnerable for gimbal lock situation. So it is better to program or represent pose using Quaternion. So Quaternion, as I told in the last class, is nothing but vector representation in a four-dimensional space where the three axes, mutually perpendicular axes, are all imaginary axes, which are mutually perpendicular to a real axis. Okay, and the quantity, any quantity Quaternion Q1 is Quaternion actually, can be represented by this one. You see, um, xi plus yj plus zk. Okay, so another quantity can be represented by z1, so x2i plus y2j plus z2k. Okay, so on and so forth. So any quantity can be represented in a generalized way. I can write down Qn equals to say Wn plus xni plus ynj plus znk, where ijk, the fundamental rule which actually Hamiltonian wrote is this one: I square equal to j square equal to k square equals to I j k equal to minus 1. This fundamental rule is followed everywhere in Quaternion. Okay, so as you know, where I equals to j equals to k equals to root over of minus 1, the imaginary quantity. Okay, now you know that I square, there is very straightforward, equal to minus 1, okay, equal to j square equal to k square. Now how I j k equals to minus 1? For understanding that, you will have to understand this one. So this is my I, this is j, this is k. Orthogonal right-handed coordinate system. Okay, and they are representing the, and then say somewhere down the line, I cannot show you because this is a fourth dimension. This is a real axis. Okay, or real axis, which is representing these W's. Now you see, they are right-handed coordinate system, so I j equals to k. Similarly, you see, I can write down so that I will not make any mistake. I j k. So I j will give you k. J k will give you I. I j j k will be giving you I, and then ki ki will give you j. Okay, and now say ijk, so I can write now ijk, right? So I can write ij, in place of ij I can write k, so k into k equals to root over of -1, root over of -1 equal to -1. So that's why ijk equals to -1, or maybe anyway. Okay, you have understood, I think. Jk equals to I, so I can write down, instead of writing this jk, I can write I, so this is I square equal to -1. So in whatever way you can compute, ijk equals to -1. Okay, so you should not try to confuse, because ijk, they are also orthogonal to each other. So property of orthogonality has to be exploited, and this is how the Quaternion famous formula was given by Hamiltonian. Okay, for which he is very famous. So understanding this, that quaternion is nothing but representation of a complex number in four-dimensional space, where this is always valid. That is I think it, to understand any problem with quaternion. Now say if I would like to add some two quantity, okay, two quaternion, right? What will be the so W1 plus W2 plus x1 plus x2 I plus y1 plus y2 j plus z1 plus z2. Okay, so this will be another uh, say composite quaternion will be of this nature. Okay, so simply you need to you need to add the real numbers. Okay, similarly minus q2 also you can do it. Okay. Now, how about multiplication? What will be the composite quaternion um, quaternion for Q1 when I am multiplying them? That is, we are going to understand that. Okay, that is very, very important. Going to J plus Z to K. Okay, and just algebra you can do. Okay, and that W1 W2 plus W1 x2 I plus W1 y2 j plus W1 z2 k plus. So I am putting this sign to tell you that now multiplication of this quantity quaternion with this real number has been already taken place. Okay, so now I am going to do this W2 I plus x1 x2 I squared plus x1 y2 I j plus x1 z2 I k 1 2 3 4. So 1 2 3 4. So these are all done. Now multiply this quaternion by this quantity. So then we are getting W2 y1 j plus y1 x2 j dot I plus y1 y2 j square plus y1 z2 j k. So it's done. Very important that you should not make any mistake. And then remaining z1k to be multiplied with this quaternion z1 w2 k plus z1 x2 k dot I plus z1 y2 k dot j plus z1 z2 k square. So this is very, very important that the sequence ij, because all we are going to do is apply this elegant formula here to make a simplified. So simplification, all remain is simplification factorization, which can be done very easily and will give you this product of the quaternion in this form, which I'm going to write. You can do that, okay, for yourself. Q1 dot Qt equals to W1 W2 minus X1 X2 minus Y1 Y2 minus Z1 Z2 plus. So this is real part, then W1 X2 plus W2 X1 plus Y1 Z2 minus Z1 Y2 I plus W1 Y2 plus Y1 W2 plus Z1 X2 minus X1 Z2 W1 Z2 plus Z1 W2 plus X1 Y2 minus Y1 X2. Okay, and that actually symbolically now we write down, okay, this is all, okay, so this is real number part of the quaternion, and these are all three complex axis part. So this real number is attached with axis I, complex axis I, this real number attached with complex axis J, and this is complex K. Okay, so this in actually simplified form can be written as W1, okay, X1 Y1 Z1 and W2 X2 Y2 Z2. So Q1 Q2 equals to this, okay, and then you can this actually can be written in the following way: W1 W2 minus X1 X2 minus Y1 Y2 minus Z1 Z2. This is a real part. This is fine, but remember these are not the merely these three quantity I am writing, they are a little bit different. W1 x2 plus x1 W2 plus y1 plus z1 y2 minus y1 z2, okay, and y1 w1 y2 plus y1 w2 plus x1 z2 minus z1 x2 and w1 z2 plus z1 w2 plus y1 x2 minus x1 y2. Okay, so this we are considering they are the imaginary portion, and this is okay, and this actually is written in this following form. This is a standard form, okay, of product of two quaternion. So now I am writing the, you see, this is a quaternion, this is a real part, and this is a vector part, imaginary part, okay, denoted by V1. So V1 is what? V1 is x1i plus y1j plus z1k, okay, and V2 is x2i plus y2j plus z2k. That's all. So this is actually, in short form, it is written like this. This is actually is written like W1 W2 minus V1 dot V2. This is the real part, and this is the imaginary part. That is the imaginary part. W2 V1 plus V2 cross V1. So this is a cross product. So this is so called. So this is, you'll have to remember. Very important for programming perspective. These are representing in this way is very, very important, and product up to quaternion is actually quaternion is can be represented by this. So this is real part, okay. So I think it is understandable to you, and this is the complex part, okay. So you can easily verify. See, little bit careful. So there are some sign changes, and don't worry. This is actually representing this. So if you do this yourself, so W1 W2 minus V1 dot V2. So you have two. So this is perfect, right? What is this quantity? This is V1 dot V2, isn't it? Because you have x1 I plus y1 j plus z1 k dot product, nothing else, plus so to the dot product x1 x2 x1 x2 and minus, so this is minus x1 x2 and then y1 y2. That's it. So this is done. This is actually this, okay, and this is what this you will have to just calculate yourself, very easy. Cross product, how to calculate cross product between, so v1 cross v2, as you know, just recapitulation, I j k, you have x1 y1 z1 x2 y2 Z2. So I Y1 Z2 minus Z1 Y2 minus J X1 Z2 minus Z1 X2 plus K X1 Y2 minus Y1 X2 blah blah. So you have got this, and these two you can calculate. So you put and you will get this. Okay. So this is what Quaternion product is all about, and it has some very interesting properties. We are going to, it follows some properties of Quaternion. Here in a Quaternion, some important property. What are those properties? It follow associative rule. That means if I have Q1, Q2, Q3, this will be equals to Q1, Q2, Q3. It is not commutative. It is not commutative. That is Q1, Q2 is not equal to Q2, Q1. And that represents, that tells you that, and it actually, um, that's the reason it can perfectly calculate the orientation of rigid body. Okay, so successive orientation in order, they are order dependent, can be captured. This is also order dependent, can be captured by Quaternion. Then its magnitude, Quaternion magnitude of product Q1 equals to, say, W1 W2 equals to Q1 dot Q2 equals to actually Z1 Y2 minus Y1 Z2 square plus Y1 W1 Y2 plus Y1 W2 plus X1 Z2 minus Z1 X2 square plus W1 Z2 plus Z1 W2 plus y1 x2 minus x1 y2 square. So this is actually the magnitude of product of the quaternion, and you will see that this magnitude is equals to just some simplification, factorization will give you that W1 square plus W2 square plus, sorry, W1 square plus X1 square plus Y1 square plus Z1 square, okay, times W2 square plus X2 square Y2 square Z2 square. So what does it mean? That means the two magnitude of the product of two quaternion is equals to, see, what is this? The magnitude of quaternion Q1 square times magnitude of the quaternion Q2 square when come out from the square root. So it is actually very important property for programmer, right? So actually magnitude of the product of quaternion is equals to the magnitude of the product of the individual quaternion, right? So is it clear? And then some few more properties. Quaternion inverse. Quaternion inverse of product. This is also very useful. AB inverse equals to B inverse, A inverse. This, okay, the quaternion follows this property. If there are so many operations like quaternion Q1, Q2 up to Qn, so inversion of that will be equals to Qn inversion, Qn minus 1 inversion, dot dot Q. So in the reverse order, you see, this is the important property, that quaternion inverse of product, okay, is equals to, in the reverse order, the inversion of the individual quaternion. So these useful properties are exploited extensively for capturing the orientation. So after capturing the orientation of a rigid body, now let us see how quaternion can be used for describing the rotation. Okay, for that let us consider an orthogonal coordinate frame. Okay, and let us consider a rigid body. So this is a rigid body, and say at any point P is a point on a rigid body, and whose description is given by the position vector OP, and here is a here is my arbitrary axis given by Q, of rotation, and about that, say we are rotating this rigid body by an angle theta. So what will be the new description of P that can be directly obtained from the quaternion? Okay, let us see. Q equals to W0 plus X0 I plus Y0 J plus Z1. Okay, then inversion of this will be equals to J minus B. Okay, and P is given by, say, Xi K. So the new description, which is given by P after this rotation, will be given by Q P Q inverse. A sandwich of quaternion operation will be done on this, okay? And you get, so extremely simple for programmer. Computer can do very easily. Then x1 I plus y1 j plus k1 k x0 I minus k0 k. Okay, so this is your q, this is your p, and this is your q inverse. So very easily you can get the description of P after rotation, so it is very useful. Quaternion is a huge field, a lot of operations and research also going on, because for describing homogeneous coordinate transformation yet to be done by Quaternion, because the description is not so compact like we want in robotics. However, for orientation, this is a very good tool, and I hope that you have now understood basic of Quaternion and how it can be used for rotation description. So thank you for your attention. Stay safe. Bye bye.